Okay? Anything converge with delta n is itself. You can show it. It's useful to remember. Anything converge with shifted delta n is shifted signal. Okay? So this means that this is equivalent to x of n minus 2 converge with delta n. Okay? You can show that as well. So, for example, I can say what would be the convolution of this signal with maybe 1, 1. So I'm saying here's the signal that we used before, 1, 2, and minus 1. I want to converge with 1, 1. Okay, let's do this two ways. The first way is using this kind of derivations, and the second way is using formula. Okay. Well, with this, what you can do is you can start here, right? This, because this is basically linear combination of delta n and shifted. Right? So, what is the convolution of this guy and this guy? Delta n converge with delta n. What is that? Is 1, right? What is the convolution of this guy and that guy? And the cell, this is delta n. Okay? Now you're here, so you center right here. What is the convolution of this guy and this one? It's 2. And this one? 2. I know it's fast. This guy, now you center at 2. This and this? Minus 1. You can sum it. Okay. This and this? Okay. So the result is going to be 1, 3, 2, up. 1. Is that too fast? Yes? Didn't get it. Let's go again.
You can find one of those things.
Doesn't matter. It can be the same. So it's just a sequence or open another sequence.
One is x of n and the other one is delta n.
X of n.
X of n. 2x of n.
Yeah, so this could be x of n. This could be x of n.
Okay.
Yes?
Don't you have to flip it or something? Where's that?
So I will do it here. See this one. Okay, I'm doing this way. Okay, so I'm trying to give you a different way of doing everything. An alternative way. The book basically give you this guy, flip and shift. It's a nightmare. Right? I'm trying to give you something that I think is useful. Okay? And this is, if you have simple things like this, it's useful to just do like this way.
It's like the vector.
Okay, so this is going to be like this. Delta n plus 2 delta n minus 1 minus delta n minus 2, right? That is the first signal converge with delta n plus delta n minus 1. Agree? That is the first one, that is the second one. Right? So, what do I get? This over with this. Delta n. This and this. Delta n minus 1. This and cut. 2. Delta n minus 1. This and this. 2. Delta n minus 2. This and that. Minus delta n minus 2 minus delta n minus 3. Right? So this is delta n 3, delta n minus 1, delta n minus 2, delta n 3. So I did here. Right? Now this way you can write, it's up to you. You may guess. If you're confused, write out like this. After a few times of this, you can do it like that. Right? All I'm doing here is, so let's go back and do it again, right? Erase this, and do it again. Here we are. What is that convolution? Now then, this guy. Here. Any questions? Back, straight. Color code. Color code. This guy. Centered one. Okay? Right here. 1 to 2 is 3. This and this is a shift. 2. It's right there. Right. That one is 2 times 1. 2 times 1. That 2 times 2. 2 times 2. Okay? Last one. Right here, center 2. What do I get here? -1. This guy is -1. Right here. Okay? Sum together like that. So now next thing I'm going to flip and shift. It's like over here. But any question on this? So if you have simple things like this, here's a few samples, that's useful to know. Okay? If you have infinite length signal, this is not possible. We have to use this. Agree? Okay. So I'm going to take the same signal here and apply this formulation and verify that you get the same result. Okay? Let's do that. So what it means here is that I'm going to fix the first sequence. So this is K. Okay? First sequence is 1, 2, minus 1. What is that? So this is K. I'll take the second sequence. I'm flipping it, right? It's minus K. Flipping it this way. And then shift it by N. Okay? So here is H of minus K. No shift. 0 minus K. This is when N equals 0. Here is x of n, x of k exactly the same, just it is x. X of minus n and minus k, you flip. So I will have this. stripping along the y-axis. Okay? Now, I want to shift this around and find y of n. Right? Y of n. So, to find y of 0, I don't shift. To find y of 1, I shift by 1, and so on and so forth. That's all it means. Right? So tell me, what is y of minus 1? If I shift this to the left by 1, that's 1 minus 1, right? It will be here. You multiply them and add. What is the multiplication of these two signals? 0. They don't overlap. Right? So that's 0. Once the first time they overlap, what is n? And the first overlap is 0. Right? This guy right here. So here is n, it's minus 1. Okay? Here is n to the 0, which is what we start out. And then look at these two guys. How many sample overlap do we have? 1. It's right there. You multiply and add. You multiply, you get 1. 0, you have 1. Times 2. Times 1, sorry. 1. You shift one more. You see this is more complicated than that? Okay? And then multiply and add. So what do you get? 1 plus 2 is 3. You shift one more. You have this times the 2 guys. Right? You have 2 minus 1 is 1. And 3, you have only one point overlap. This guy minus that guy, right? It's minus 1. I know, you gotta practice this. It's not easy. Okay? Let me pause for question. Basically, we fix one sequence. The second sequence, we flip and shift. How much do we shift to give you the value of output? Okay? So we shift minus 1, minus 2, all the way to infinity. There'll be a certain point that they don't overlap for this case, which is one is less than and equal to minus 1, they don't overlap, therefore everything out here will be 0. If more than 3, don't overlap, therefore it's 0. Right? They overlap from 0 to 3. So you basically just shift at 0 time, it's right here. Multiply, add. So 1 times 1 is 1. This guy, 2 point overlap, you get 1. There's 2, it's 3, and so on. When it's quiet, I'm worried.
I just feel like I'm right on the cusp of getting it. Can you just say
One
that
more
last
example?
part one more?
Wait, one more example.
Yeah, just
Okay, so
steady
one more,
through
right.
it. Because I was copying down what you were writing. Can you just step through the multiply adds?
Okay, so let's do one more example. I think that will be making clear.
Okay.
Okay?
Fine.
So let's do this example. And go over to 7. Okay? what do you think the output's going to be? Triangle. Perfect. So now we're going to output to be triangle. Let's verify it. Right? So what is the process? Keep this one the same. Let's do it K. Right? This guy I'm going to flip. So I can call this is x of n, x of k, h of n, x of minus k. Right, we shift. So now we're going to shift this guy around, and what are the overlap, and so on and so forth. So tell me a shift and there's no overlap. Negative value, right? So I shift this to the left and the left value. There's no overlap. So I know that the output is going to be 0 for negative value. That something happened at 0. Right? So when n equal to 0, what we have? Just this guy right here. There's no shift. It's 0 minus k. And equal to 0. How much overlap do we have? One overlap. Right? So 1 times 1 is 1. That's it. Everything else is 0. So the output is going to be 1. What's the output at time 1? We'll shift this to the right by 1. This is n equal to 1. Will be fine. And how much overlap do I have? At 0 and 1. Right? At 2 have overlap now. 1 times 1 is 1. 1 times 1 is 1. The sum is 2. Okay? You have 2. What's the value of 2? 3. What's the value of 3? 4. Okay, good. Now what's the value of 4? 3. Because the maximum overlap is 4. Right? So when they start like this, they have less overlap. And then because they are both symmetry, you know what's going to happen. This one will be like this, in symmetry. So it'll be 3, 2, 1. Okay? And the next example will be exponential function. Okay? That's what we need to do. Yes?
Before you get into that, talk about what the two U's are.
What are the use of this?
Yeah, what is
This is used. So before Fourier transform, the next thing we'll talk about is doing all this using Fourier transform, which is what we're using right now. We're hardly doing any of this convolution, right? But we use Fourier transform. But this is useful to actually know how to compute.
What I'm saying, what I'm asking, what is the statements? Which one, a sample of something you recorded, and the other one was an algorithm and you wrote?
It's the input, yes,
Or-
yes.
Okay.
Yeah, so we can think what he's asking here is, what is the context of this, right? So it's basically, so what we have here is, LTI system, we have impulse response. And we're going to talk about how to find this later on. Okay? Once you have impulse response, you can use this technique to find output for any input.
It seems like the output's a linear combination of several past values.
Yeah.
That's all the combination is.
That's right. That's right. That's right. Now, the difficulty here is how to compute for that, right? How to compute this summation. This is why we hardly use convolution to find the output. We use Fourier transform. Okay? Because this kind of manipulation is it's hard to program or it's hard to work with. But MATLAB actually have convolution, and that's what MATLAB is good for. Right? If you have a signal like this, that's what to do. It basically is multiplied like this. Just index. Okay. So one other way you can think of this is using matrices. So let's think about this, right? Let's go back and look at this. The okay, it's 1, 2, minus 1. The matrix that you have here basically a bandit of this guy. So it's actually 1, 1, 1, 1, 1. So if you think about this, right? If you have this 1, 3, 1, and then minus 1. Okay? So basically, you can do this way and you do the matrix way. And so I can take 0 here, you can put 1, 1 like this, and it's kind of time 0. Right? It's kind of time 0. So another way to do this, a way that MATLAB is doing it, is basically using matrices like this. You can have the input like this. So this is x of k, right? That's the one we don't flip and shift. It's like here. Okay? This, when you do this way like this, that you are shifting. You shifting this. You are shifting this. And multiply. Multiply here is basically matrix multiplication. Add. Right? Now this is symmetry. So you don't see the flip. Okay? However, if I have another example where do the same thing, okay? So that guy, if I go this way, okay, minus 1 here. What could be the corresponding matrix? Going from 1, 1 to 1 minus 1. What would be the corresponding matrix? Same vector, same input. 0, 1, 2, minus 1, 0. Okay? Times 0 here. What could be the corresponding row here? See, you have to flip. You have to flip. So it's minus 1, 1. Times 0 here. Okay, then minus 1, 1. Minus 1, 1. Minus 1, 1. Like that. That's another way we visualize convolution. Right? We fix the input, x of k. This guy, we flip h, then we shift them, multiply and add. The multiply and add is the matrix multiplication. Right? The shift in here just gives you different how much you shift is where you are in y. So here's your output, y. So, time 0 is here. Right, time 0 is the first row. Is that clear? Okay? So I'm giving you, three different ways of doing convolution. Okay? So just review them again, right? The first way is just point and point multiplication. Second way is graphical, right? We flip and shift. And the third way is how MATLAB does it. It's by matrix and vector multiplication. Is that clear? Yes? Okay. So let's talk about frequency. Okay? All of this is useful, but then it could be complicated. And we need to bring in Fourier transform into the discussion. So I'm going to discuss Fourier transform very quickly, and then we'll continue on the next lecture. Okay? Let's look at Fourier transform. I complain about coffee, it actually brings coffee up. It's good. Let me tell you to bring water. Okay. So how do you derive discrete time Fourier transform? Is green visible down there? Yes? Who remember how to derive discrete time Fourier transform? Who remember what it is? What is h of e to the j omega? Okay. H of k e to the minus j omega k. Right? That's the definition that we all know. But who knows where is it coming from? So, suppose you want to derive it only based on what you know so far. Like the system, convolutions. You say, my lecture is always deriving it, right? I want you to remember why, where things come from, not from this definition. Okay? So tell me, based on what we know so far only, how do you actually find that expression? So we know LTI system, right? So go back to freshman year, many years ago, in the lab. They give you a black box, right? And they want you to know, analyze the black box. What's it doing? What is the first thing you do? They give you a signal generator. You create a sine wave, you feed the black box and see what's going on out, right? Let's say we tune the frequency, doing something, and then suddenly it drops out of zero. You can tell me what the black box doing? It's a filter, right? So it's basically passing the signal and it's go to zero. No, it's working. It's not a blackout thing, right? So basically you have sinusoidal in there. Okay? So let's do the same thing here. I'm going to poke, right, at my LTI system that I know how to define using a certain frequency. So let's say I want to write S of n equal e to the j omega naught n. Omega naught can be anything. Time 2, anything you want. Some frequency. And I want to know what will be the corresponding output. Okay? So I know that my LTI system is going to respond to x of n. I can write it in terms of x of k, x of n minus k. This is convolution. We just derive it there. Right? This is true for any LTI system. So the input response x of n. In particular, this is my signal. What could be the output? Now let's plug it in. Summation in k, x of k, e to the j omega naught n minus k. Right? So how do I simplify that? This one is a product of two exponential. The first one is e to the j omega naught n. The second one is e to the minus j omega naught k. And the third depends on k, can be pulled out. Agree? So it's going to be summation, sorry, e to the j omega naught n, summation in k, x of k, e to the minus j omega naught k. That's interesting. For a sinusoidal, the output is actually an input. That's the input. Comes something that independent of the input. Only depends on the system. H of k. Right? And that's what we call it transform, transform of the system. H e to the j omega naught k. Exactly like this. That's how we're discussing Fourier transform. So we introduce Fourier transform. So it means that I can actually, with LTI, I can measure this by input exponential, sinusoidal. Right? I can measure this. I know exactly the output's going to be. Because the output's going to be the same as the input of this. I know the input. I can measure the output. I can measure my system response. Agree? Now I'm varying omega naught. Low frequency is 0 to pi. And I'm plotting out the frequency response. This is a complex quantity. So with magnitude and phase, right? I can measure all of this. If it is a low pass filter, it's going to be low passing, right? I can have signal back, and boom, go to 0. It's high pass, it's going to be nothing, and coming out, and so on. Okay? So this guy here is called eigenfunction of LTI system. This looks like an eigen system, right? The output is an eigen, so this is basically that's how you set up, right? It's the scalar, it's like eigenvalue of the system, and so on. Okay? So that's how we define Fourier transform. And this is very useful. With this definition, I can derive the corresponding input and output relationship. I can use the same definition for x. Basically, x, e to the j omega, summation in x. Right? Same definition for y. And I can derive this quantity. And this is now very, very useful. That's how we basically do it now, right? Signal in, we look at the spectrum, we multiply the spectrum, and we basically manipulate the spectrum. Okay? Yes? what's the eigenfunction? So this is the derivation, right? The eigenfunction. So if you remember in matrix theories, how do you define eigenvalue or eigenvector? So you have a matrix A. If V is the eigenvector, what is it? How do you write the equation? A times V equal to lambda times V. Right? So what you have here is lambda times V. Okay? So basically, this will be your eigenvector, eigenvalues. This will be basically eigenfunction. Okay, so similar to the notion of eigenvector and eigenvalues in matrix theory. Yes.
Something's not quite right. Not sure if I'm missing something.
Okay.
But you have, I think you have tables in somewhere.
Where is it? Yeah. Yeah.
So the derivation of top.
This is the definition that we normally give it.
Definition, right? H of E, J of omega
Mhm.
equals value for K to infinity.
Yeah.
So with K being part of the
Explanation.
exponential.
Yes.
And then down here, down one more.
Oh. Thank you. Yeah. Thank you. Yeah. So this is just okay. Thank you. Okay. I know I'm going a bit over the limit, but I probably. So any question regarding this derivation? Good. So let's take a look at this, right? This is a complex quantity. A complex quantity can be represented in terms of magnitude and phase. Okay? So we can write h of e to the j omega into magnitude times the phase response, right? How do you find magnitude response of a complex number? Absolute value, so basically square root of imaginary part square plus root bar square. How do you find the phase? Arctangent of imaginary over real. Okay? Alright, we'll take a break now. Okay? Hopefully after the break, 10 minutes, we'll go back and then we'll cover the discussion problem. So what we have outside these with water outside from.